Anyway, so this first content is what do we mean by actual austenite grain size? So let's see. This is what I have taken. I have taken the iron temperature diagram thinking. This is the temperature axis, and this is the weight percentage of carbon axis, right? And I have chosen eutectoid composition, that is 0.76. Okay, so that means initial microstructure is 100% perlite you have, right? And you want to make it into austenite phase, right? So what you need to do, you need to take it above A1 just. The moment you take it above A1, austenite will start forming. And already we have discussed that, nucleation of austenite and growth of austenite, we know it, right? But the condition is just imagine, I will choose one composition, I will choose one temperature here, and I will choose one temperature here, and I will choose one temperature here also, or maybe somewhat around here, right? So these are the 4 temperatures I have chosen. You see? T1, T2, T3, T4. Okay. Now you want to check the grain size of the austenite. So that means you want to check the size of the grain, for example, here and this one. You want to check the size of the grain. So can you tell me what will happen to the size of the grain? If you choose, yeah, what will happen? It will become coarser, of course, right? So for example, maybe this is like this. This may be like this. This may be like, and this may be like, okay, fine. So that means the moment you are taking the eutectoid steel just above A1, but which is the lower critical temperature, austenite will start forming, right? But the size of the austenite will change if you choose a higher temperature from A1. Okay. More you go to high temperature, more will be the size of the austenite grain. Okay. Similarly, it also depends upon the holding time. Suppose you choose a particular temperature, but you allow the steel to stay for 2 hours. You allow the steel for 4 hours, 6 hours. So more you allow it to stay for more hours, the grain will become coarser. That is because of diffusion only. Because you remember diffusion based transformation, right? But what is changing? Number of grain boundary is changing. Just see. Higher you you are moving to a high temperature, the number of boundaries is decreasing, right? But the size of the grain, individual grain is increasing. That is the point. Okay? And that size is actually called actual grain size, or you can also call original grain size or actual grain size of the austenite. Okay. It is very simple. Just room temperature phase, you just converting into austenite, and the size of the austenite grain is called original grain size of the austenite, or original size of the steel sometimes. Grain size of the original. Original grain size of the steel you can also say. Why they are saying this? This is the original size of the grain size of the steel, because that grain size will affect your final product grain size also. That means, suppose you start with this austenite and you again move to room temperature. Okay, that means from T1, T4 to room temperature, T3 to room temperature, T2 to room temperature, T1 to room temperature. So what will happen? Your product will be same perlite, 100% perlite will form, right? Ferrite will be there and cementite will be there. But if you see the grain size of the ferrite, and if you see the grain size of the perlite, otherwise the distance between the lamellae, it will be different. In other words, I can simply say, lower is the transformation temperature, finer is the size of the grain produced. Okay, that means when you do transformation from T1, you end up with very fine grain size, or you will end up with fine perlite. But if you start the transformation from T4, you end up with coarse perlite. So how this is getting affected? Because of the size of these grains. So that means larger is the size of the austenite grain, larger is the size of the product grain also. In other way, smaller is the size of the austenite grain, smaller is the size of the product grain. So whatever product grain will form, that size actually affected by this austenite grain size. So that means what is the recommendation? What you are going to recommend for the heat treatment? Can you tell me now? No, yeah. So that means you have to do austenitization, but at lower temperature, not so high temperature. But you have to see the requirement also. That means the austenite which should form should be homogeneous, right? It should be homogeneous austenite. There should not be any residual phases remain. Only austenite phase should be there. That will transform into any products, like perlite. It will form at the end, right? You need to form homogeneous austenite. Second condition is the austenites we should form should have finer grain, so that when transformation will happen again, you will end up with finer product grain also. And you know, finer grain size have good strength or good toughness also. That is the main point. So that's why that is called original grain size of the austenite. Okay, is it fine? So the weakened austenite affected by two things. One is affected by temperature of transformation above lower critical temperature here for basically this kind of steel, and the one is the holding time. So temperature of transformation and holding time will affect the grain size of the austenite. Okay, this is very simple, nothing to do. Okay, fine. So next is mechanical property affected by. See, we are studying heat treatment because we have to change the mechanical property. We have to improve the mechanical property. So basically there are four mechanical properties which will be affected by the grain size. Final grain size of the product or grain size of the austenite. Okay, anything is fine, whatever you say. So first one is the strength. Your yield strength and tensile strength will be affected by size of the austenite grain. So finer is the austenite grain, higher is the yield strength, higher is the tensile strength. Coarser is the austenite grain size, lower is the yield strength, lower is the tensile strength. That is one important one. Second is the toughness. Already we have discussed now properties, toughness property, right? So toughness also improve if the size of the grain is smaller. So finer grain size will give you more toughness. Can you people tell me one example where we need very high toughness in any application? Just give one example. Maybe we have discussed that already. Railway tracks, yeah, fine. Gears, rolls. Basically, toughness is important where there is impact loading. Loading is impact and sudden. Like bulletproof jacket, for example. Bulletproof jackets. You want to have a bulletproof jacket because bullet is moving with a very high kinetic energy, right? High velocity and high kinetic energy. The moment it will impact, it will strike. The bulletproof jacket should absorb the energy without any fail. But if it cannot absorb it, then bullet will penetrate easily. So where there is impact, when sudden loading is there, in that condition you need basically what? High toughness. That's why you are doing, okay, so maybe HOD sir is teaching you what testing of materials. Maybe you're going to do one experiment in the downstairs. We have one impact tester, Sharpie impact tester. There you can see that particular load will just hit it at a very high velocity, impact. If toughness is good, it will just bend. But if toughness will be poor, it will break. Basically, actually we want to break it to see the morphology and different properties, how much energy it is absorbing. Anyways, fine. Next is machinability also. Machinability is also a very important property that will be affected by the size of the grain. What is machinability? Basically, you have undergone this workshop, I think. So you have seen the lathe machine, right? Lathe machine, right? So what we do in the lathe machine? We take out chips, you have seen now. We want to do machining means we want to do surface finish, good surface finish should be there. So we want to produce some chips out of the material, right? Chipping. So in the chipping process, if chip is continuous and chip is discontinuous, which one we need basically? Continuous, are you sure? Discontinuous chip should be there, then it is easy. Machining is easy means discontinuous, when chip will form and break. Otherwise, if it will not break, it will elongate to a long distance, right? It will, because that means plastic deformation is happening to a long distance, right? So the point is, good machinability means discontinuous chip should form. The chip will form and break, right? It a cutting action kind of. It will form and cut, right? Again it will form and cut. But if it will not cut, it will move to a long distance. Okay. So the point is, you can justify like for good machinability steel, One condition is your tool should not get wear with time. The tool is very expensive actually, tungsten carbide, it is very expensive material, right? Tool wear means, because chipping action means that is a wear action, no? You know wear already, I think. Wear means when there is a relative motion. One is fixed, one is moving. There is a relative motion between two bodies in contact. So what will happen? Some material will get eroded from the one surface. Okay, fine. So basically erosion should happen on the material. It should not happen on the tool. Right? If tool will be weaker, erosion will happen, right? So basically good machinability steel means less wear will happen on the tool. Actually we want a good machinable steel, then only machining will be easy. Tool wear will be less. That is one point. Second one is some force or pressure is required because lathe machine is moving to and fro, right? So if force applied is more or power consumption is more, that means poor machinability. Steel have poor machinability. Less power means good machinability. And the last one I told, chip may be continuous, discontinuous. If continuous chip, poor machinability. If discontinuous chip is forming, it is good machinability steel. So that is affected by grain size. Okay, you understood my point? And there is another concept called hardenability, and that is the most important concept in heat treatment. That is a complete one class lecture or two class lecture. We'll discuss that. 2 to 3 lectures. And you are going to do one experiment also in the lab. Hardenability, quench, Jomini, already done?
Today we did it.
So you have more knowledge than me right now. Anyways, fine. Okay, so anyways, I am not going to ask you question right now. Anyways, so my point of view is hardenability is a very important property, and that property is affected by the grain size also, austenite grain size. So austenite grain size will affect the strength, it will affect the machinability of the steel, it will affect the hardenability also, and also toughness. These are the 4 important mechanical properties affected by the grain size of the austenite. And we always need good hardenability, good machinability, good strength, right? Good toughness. All should be in a good shape or good, like in a high value, right? So that is the need we are doing heat treatment again, to improve the toughness, to improve the strength, to improve, somewhat, so not exactly soft, it should be intermediate actually. Okay, let me discuss otherwise. If you have asked me the question right now, okay. Suppose you choose 2 kind of steel, one is having finer grain, one is having coarser grain. So what do you think, in which case steel will have more machinability, good machinability? Finer, okay, you know that. Coarse, finer. Actually the real answer is coarser. Real answer is coarser. Why I am saying? Because finer grain steel means the steel have both high strength and high ductility, both. So you have to remember, toughness exactly means the steel have both property. It has good strength and good ductility. But strength and ductility are always opposite. But finer grain we are producing because we need good ductility also and good strength also. Because we want to have a steel which can withstand the impact load, sudden load. Obviously strength should be good, and if crack want to initiate, it cannot initiate because deformation will happen, because ductility is also there. Just imagine the situation. Suppose sudden loading is happening, sudden impact, right? The moment the impact will happen, so what will happen? Deformation may start, also crack may initiate. So if deformation is there, crack will not initiate actually. If a small crack also initiate, crack blunting will also happen. You have studied this, I think, blunting of crack and all. DVM, how you can say? Okay, maybe. Okay, sir will teach you otherwise. In testing of materials, it will be there. Maybe. I'm not sure. Okay, graphite theory, you haven't studied. Graphite theory, okay, anyways. Maybe in fracture mechanics or testing of material. Coming semester maybe. Okay, anyways. So if a crack want to initiate, the crack will not propagate. It will stop due to plastic deformation. Plastic deformation is due to ductility. And you need also strength now, because impact loading is there. You need also strength. Strength means resistance to deformation again. So both things are present in finer grain material. Okay. So that means exactly, okay, if people know dislocation motion and all, at least you know, right? So if the grain is a coarse grain, so what will happen if dislocation want to move and you want to deform it? So a time will come, lot of dislocation will generate and they will pile up at the grain boundaries. You know all these things, right? Like this, right? Grain bound pile up. So coarse grain and fine grain, for example. And suppose this is coarse grain. The dislocation is moving in this direction, right? And finally, for example, a lot of dislocation will come and stay here, right? So this is called dislocation pile-up. Dislocation want to glide, but they will interact a grain boundary. Okay, the moment they will interact a grain boundary, they cannot go to another grain. They will stop there. Okay, so that is called piling of the dislocations. So due to dislocation pile-up, what will happen? Dislocation interaction will also happen, right? There is a back stress will be happening. One dislocation will apply stress on the dislocation, like this. That means this dislocation will apply stress on this will this, so they cannot move further. But still deformation is happening. How? New dislocation will form in the next grain, and that will move. Frank-Reed source. I think you have studied this Frank-Reed source at least.
Yes, sir.
Okay. Generation of new dislocation. Pinning of two dislocation, then you apply load and it will come out. Already you have studied. Okay, very good. So just imagine you have finer grain material and dislocation is moving. So what will happen? Lot of grain boundaries are available. So that means dislocation will form and they will pile up in a, like what I can say, like in equal manner they will pile up. Suppose two dislocation will pile up along one grain, two dislocation pile up in another grain. So multiple dislocation will pile up in multiple grains, right? So amount of strain is uniformly distributed, there is no issue. But here less number of grain are there. So lot of dislocation will pile up in one single boundary, you can say. Two single boundary. So stress will be more, fracture will start. That grain boundary will fracture. So that's why it help you in what? In easy machinability. Coarser grain have good machinability, that is the reason. Do you got my point? But in this case, lot of dislocation will generate, but they will distribute throughout the material. But less number of grains, more dislocation will generate in one grain boundary. So obviously more stress will be applied on the grain boundary, it will fracture. And we need discontinuous chip, that is good machinability, no? That means chip will come out. Rather than deformation, it will come out. But in this case, finer grain material, deformation will occur. It will produce a continuous chip, which we don't want. Do you got now the point? Okay, I think. Anyway, since hardenability we will discuss in coming lecture maybe. Okay, this is important. You might get a question from this. Steel classification on the basis of grain size. On the basis of grain size, whether the grain is coarser, finer or whatever. So we can have a classification of steel. That is called inherently fine grain. One steel is called inherently finer grain steel, inherently coarser grain steel. You can write. Two kind of steel. Inherently fine grain, inherently coarse grain. Inherently fine and inherently coarse. Inherently fine grain and inherently coarse. So inherently fine grain steel means, this is very interesting, listen it carefully. So you start with suppose a hypoelectrolyte steel maybe, okay. So you have an original grain size of the perlite and perlite grain and as well as your ferrite grain, right? You start heating it to high temperature. Now you are forming austenite, complete austenite. So austenite have a particular grain size, okay, we already have discussed that. But during this kind of heat treatment, sometimes the grain will not become coarser even you are going to a high temperature. Suppose for example you are going to temperature around 1050. Grain will not become coarser. Still temperature is high, but coarsening of the grain will not happen. And that kind of steel is called inherently finer grain steel. But if the steel is inherently coarser grain, the moment you are going to high temperature, for example 900 degrees centigrade or 850, it will start coarsening. More you go to high temperature 900, it become more coarser. 950, it become more coarser. 1000, it become more coarser. 1050, it become more coarser. It cannot, that means the grain boundary is moving, right? I mean the grain coarsening is happening, right? That is called inherently coarse grain steel. But if the steel is resisting the grain growth, even at high temperature, that is called inherently fine grain. So now can you tell me, you people know this already, we have discussed all these things. How this is possible? One steel is resisting the grain growth, one steel is not resisting the grain growth, it is growing. What may be the reason? You already know this. Already it is written also there. You can also see. Alloying additions. Right, alloying additions. Very good. Which alloying additions? You already know this already. Huh? Sorry? Vanadium. Okay, very good. Vanadium is one example. Any other? We already have discussed about ferrite stabilizers. Ferrite stabilizers are very strong carbide formers. And carbides are precipitates. They will form along the grain boundaries. Right? Vanadium, good example. Niobium is good example. Titanium is good example. Tungsten is good example. Chromium is also good example. Yeah.
Sir, alloy of vanadium and nitrogen.
Yeah, that's not exactly alloy. It's you are adding one element, and because of presence of nitrogen, it is forming an carbides or nitrates. Anyways, so you understood my point. The basic example is okay. Already I think it is here. Heat treatment at high temperature. Okay, we'll discuss about this one, then we'll discuss about this one, deoxidation. So that you can simply write, because of presence of certain alloying elements which form stable carbides, stable nitride also, or stable oxides. And these carbides, nitrides and oxides, they basically segregate along the grain boundaries. Because of segregation of carbides, nitrides and oxides along the grain boundaries, what it means? They are actually pinning the grain boundary. Grain boundary is pinned. It cannot grow. You understood my point now? Suppose this is, for example, this is grain boundary. So they will form like this. They will form like this in this region. These are precipitates, you can say, or oxide is a dispersoid, if you remember, I told you. Oxide is a dispersoid. But carbides, nitrides, you can call it as a precipitate simply. Okay. So they will form along the grain boundaries, or you can say they segregate along the grain boundaries. Indirectly I am saying they are pinning the grain boundaries. Suppose, for example, if you increase the speed of the fan, for example, your notebook will start, your pages of the notebook will start moving, right? But if you apply one pin to your pages, right, you can increase the speed of the fan, but it will not move. That means same thing happens here. Grain boundaries is pinned. It cannot grow. Is it fine? So precipitates, dispersoid, like carbides, nitrides, oxides, they pin the grain boundaries. Or they basically precipitate along the grain boundaries, so grain boundary coarsening will never happen. So you understood, by addition of alloying element, we can prevent the size of the grain, even at high temperature, around 1000 to 1050. Okay? So that is inherently fine grain steel. Alloying element you understood. Similarly, you didn't ask, nitride also forms. So there are some alloying elements which form stable nitrides, like titanium nitrides. I worked on that steel during my MTech. Titanium modified like power plant steel. I worked on that. Titanium, if you add titanium, titanium will form titanium carbide, it will also form titanium nitride. Titanium nitride is very stable, very small and very stable. Very small precipitate forms. Another one is, for example, boron. People add boron into the steel. It forms boron nitride also. Boron nitride is also very stable and very strong. Right? So boron addition, titanium addition, they will form stable nitrides. They pin the grain boundary. Is it fine now? You got it now? So that is the reason why the coarsening of the grain will not occur at high temperature. But do you think it will happen for long, very high temperature? No. If you go to a very high temperature for 1200 degrees centigrade, what will happen? These precipitates will get soluble in the matrix of austenite. So once they become soluble, no, nothing is there to pin the boundaries. So coarsening will start. So it doesn't mean you cannot, it doesn't mean that you can stop the grain growth at very high temperature, around 1200 degrees centigrade. It's not possible. But around 1050 is fine. Now I think you understood this one. Then there is another concept, see, deoxidation. I have written how deoxidation helps in hot working and heat treatment at high temperature. Okay, fine. Okay, maybe you will study this deoxidation during your steel making subject. Steel making subject is in the next semester. Okay. Okay, let me tell you a small part of that. What exactly deoxidation means. See, the first stage of production of steel is iron making, right? We produce iron from the ore. Fine? Because we already studied mineral processing now. We do mineral processing, finally you will get a concentrate of iron ore. That concentrate of iron ore will be extracted, iron will be extracted from that. That is molten iron, pig iron we call it. That molten pig iron is impure one because it contains carbon, it contains silicon, sulfur, phosphorus, manganese. Lot of impurities are there. And steel making means you have to remove all these impurities. You have to remove this carbon, you have to remove the silicon, phosphorus, sulfur. All these impurities can be removed during steel making process. So iron making process, then steel making process comes. And that's why people call steel making is a refining process. Because we are removing the impurities. But iron making process is the extraction process. We are extracting the metal. But that is the impure metal. Do you got the point? So how to remove these impurities? We are intentionally supplying oxygen into the process. So what will happen? When you provide oxygen into the molten pig iron, this contains impurities and these impurities have very high affinity toward oxygen. So they react with oxygen and form oxides. Carbon will form oxide, silicon will form SiO2, phosphorus will form P2O5, like this they will form. Carbon will remove in form of carbon dioxide, carbon monoxide as a gas phase. But P2O5, SiO2, they will goes to a slag phase. Because they are very stable, they remain in either solid or liquid phase. Do you got the point now? So that is called, so during this process what will happen? With the time, impurities will be reduced. But still you are providing oxygen. So a time will come, the concentration of oxygen will increase in the molten steel, which is not good when you do casting. Because next stage is you need to do casting. So that you can do rolling, hot rolling or cold rolling. You have visited the industry, you know, people know, right? So the moment you do casting, what will happen? Casting defects will come out. Blowholes, surface blows, porosities, pinhole porosity, you will know this. Some defects will come. That is not good actually. And due to presence of oxygen, sometimes oxidation also happens. Your surface finish will be very poor. Nobody will buy your products if surface finish will be poor. So you need to remove the oxygen. And that removal of dissolved oxygen is called deoxidation actually. You got the point how I am correlating? So removal of dissolved oxygen in the steel is called deoxidation technique. So how to remove the oxygen now? The question is now how to remove. Vacuum, yeah, he knows that, vacuum degassing. But it always, okay fine. But basically to remove oxygen, we do deoxidation, not vacuum. Vacuum basically used to remove nitrogen gas and hydrogen gas. But to remove dissolved oxygen, we do deoxidation. That is not a vacuum process basically. Not a vacuum process. We add some alloying element, ferroalloys, like ferrosilicon, ferromanganese, ferrotitanium, something we need to add. And those ferroalloys we need to add, which have very high affinity toward oxygen. Because they will go and take away the oxygen from the molten steel. Right? This is very interesting. See, you want to remove the carbon during steel making process. Again, you can add carbon to remove that same oxygen. And that will be advantage when you are producing high carbon steel actually. Right? You need to add obviously high carbon to get high carbon steel. That carbon also form carbon monoxide and it will remove, oxygen will get removed in form of CO. Very interesting. You can add titanium also. It will form TiO2. You can add aluminium also. And in the gate exam sometimes they ask, which is the most strongest deoxidizer. Aluminium is the strongest deoxidizer. Just by adding aluminium, you can remove a lot of dissolved oxygen. You can bring it to ppm level. You just imagine. Just by adding, and aluminium addition is always done in virgin form, not in ferroalloy. Why? Because iron and aluminium do not form any alloy basically. Because solubility of aluminum is very less in iron. So they are added in virgin form, directly aluminum. But you want to add titanium, then add ferrotitanium. You want to add silicon to remove oxygen, you add ferrosilicon. If you want to add boron, ferroboron. Right? Do you got the point now? And aluminum is the strongest deoxidizer. You can reduce the amount of oxygen to ppm level. Sometimes ppb if you want, that can be done. But can you tell me what is the problem now? If you add aluminum into the steel to remove dissolved oxygen, oxygen will remove in form of Al2O3. But what is the problem now? Just you know the answer. Yeah. Because aluminum will be no. Solubility of aluminum is less. The function of aluminum is to react with oxygen to form Al2O3. But some Al2O3 will trapped in the steel. You got the point? All the aluminum oxide cannot be removed. You got the point now? So that aluminum oxide will again segregate along the grain boundaries. That will pin the grain boundaries. So it is helpful also. But the condition is the amount of aluminum oxide should be less. And it should be spherical also. And that aluminum oxide is actually inclusion. I think I told you this inclusion part maybe somewhere. I don't remember. But inclusion in steel. Inclusion in steel is very dangerous to steel. But it can be beneficial if the amount is less and it is in spherical form. Basically. But if it is needle shape, then it is a problem. If it is elongated shape, it is a problem. Why? Concentration of stress will play there. The concentration of stress will be different. But if it is spherical, stress distribution will be uniform. So no problem. So do you got the point? So deoxidation also help you to maintain the grain size. The grain size will not become coarser with temperature because of formation of aluminum oxide. So this is very interesting. See? I think this part is clear. And this is also done. This is a question from my side. Now I am telling you. Question number, this is actually 6, but I have written 7 anyway. How the property of two steel will be different with same composition, same heat treatment. See, don't answer me, just raise your hand please. So question is, you have two type of steel. Both have same composition, same grade. And you are doing same kind of heat treatment. Same kind of heat treatment means you will end up with same kind of phases or same kind of microstructure. Basically. So how the property will be different? Just please raise your hand, don't answer. You got the question now? Composition is same. So property should be same, of course. And you are doing a heat treatment process where it is same heat treatment. So you will end up with same kind of phases. So now how the property will be different? Just imagine what can be theirs, that's how property is different. Just raise your hand. Okay, only 2 people. Forget about the defects. Both have same kind of defects otherwise. Fine. Same kind of defects, alloying. Composition is same, no? How alloy? Reduction ratio. What reduction ratio? Shape. Okay, both have same kind of shape. Dimension is same, everything is same. Grain size. Size of the grain. Just in one case, size of the grain is small, one case, size of the grain is bigger. But composition is same. Same carbon, same alloying element. Same heat treatment, same kind of phases. But morphology is also same. Suppose spherical morphology, whatever is forming. But that means grain size is different. You can write, maybe you can get a 1 mark question from this or 2 marks. Direct question. In the end semester maybe. No? But the question may be not direct, somewhat in a different way. So grain size, now this is a question, I think you also have studied this one. Tell me now, grain size versus yield strength. Can you write a relationship between grain size and yield strength? Hall-Page relation, can you write it? You can write the equation. I want to see the equation. The relationship between the yield strength and grain size. How yield strength will be affected by the grain size. You have studied this in DBM maybe. Hall-Page relation, yeah. Sigma y is equal to sigma I k constant d to the power minus half. Or root over 1 by root of d, whatever you can write. Right?
The plus.
Yeah, good. So this is the yield strength actually. This is sigma y is the yield strength. That is affected by d to the power minus half. D to the minus half, but 1 by root over of d. So that means 1 by root over of d means it is inversely proportional. Sigma y and d are just C inversely proportional. Fine? That means smaller is the d is nothing but the average grain size. Okay. So that means if average size of the grain is smaller, sigma y is more. If average grain size is bigger, sigma y will be less. So yield strength is affected by the average grain size. Finer grain have more yield strength, coarser grain have low yield strength. That is the relationship, you know that. This is important now. Equicohesive temperature and creep. Creep may be, I think, okay, maybe next semester you have a subject, I think, fracture mechanics, I don't know. Maybe you will study that. Okay, let me tell you it quickly, very quickly. So creep is a one kind of failure mechanism, just remember. Creep is a one kind of failure mechanism. Material can fail due to creep. And this basically happen at high temperature. It can happen in low temperature also, but basically happen at high temperature because of two reasons. One reason is diffusion, because we know that more we go to high temperature, more is the diffusion rate. Atoms and vacancy will move in opposite direction and it will improve. Okay, that is one point. And second point is, at high temperature, grain boundary sliding happens. One grain and another grain, they will slide past each other. They will move. They will move means what? Plastic deformation is happening. Grain boundary crack will not happen. Crack in the grain will not happen, but they will move. One grain will slide past another grain. Right? Like sliding is happening. That is called grain boundary sliding. So because of these two reasons, one is high diffusion rate at high temperature. Second one is due to grain boundary sliding. One grain and another grain which are in contact, they slide one past each another. That means they are flowing. They are like moving. That means plastic deformation is happening. That is actually called creep. Condition is what? Temperature should be high and load should be constant. You have applied a load on the material that is constant. And another condition is there. The load is below the yield strength. Very low load you have applied. See, we basically know that what? We basically know when the stress will above the yield strength or yield stress, plastic deformation will happen. We know that, no? The moment you are applying a load and stress reaches the level of yield stress, then plastic deformation happen. But in creep, you have applied a load, but stress is very less, below the yield stress. But still plastic deformation will happen. Condition high temperature, and another condition is load is constant. Time interval is also too much high. Maybe some 5 years, 10 years, like that. Or maybe 2 years, it depends. So that's why people call it is a catastrophic failure. Creep failure is a catastrophic. It will not give you any kind of indication. Material, because you cannot see the deformation. Inside deformation is happening, you cannot be able to see, visualize it. Because it is so slow. But it will fail. A time will come, it will fail. So basically when your application area is very high temperature, creep failure is the maximum chance is there. So you have to increase what? Creep resistance. Some steels are called creep resistant steel. Best example, super alloy. We have discussed that maybe, remember. Super alloys are used because it has high creep resistance. You remember the super alloys? Iron based super alloys, nickel based super alloys and cobalt based. These are three elements, iron, nickel and cobalt. Anyway, so we will not go into that right now. This is fine. This is what is equicohesive temperature? This concept is very good concept. You may get a question from this also. What is equicohesive temperature? So I can say what? Suppose I have one material. So this is what? GB and this is the grain. Okay? Or people call it as matrix also. If you want, you can also write matrix. Two things are there. You take any crystalline material, maybe steel. So steel have grain boundaries and grain, or it has matrix and grain boundary. Two things are there. So what happened? Two things are there. Grain boundary is one and matrix is one, or grain is one. But this is very interesting. at room temperature, grain boundary is stronger than grain. Very interesting. But if you go to very high temperature, grain boundary become weaker, grain will become stronger. This is a very interesting point phenomenon, you have to remember. Again I am saying, so that means equicohesive temperature is that temperature when the strength of the matrix is equal to strength of the grain boundary. Again I am saying equicohesive temperature is that temperature when strength of the grain boundary will be equal to the strength of the matrix here or strength of the grain. They will become equal. Similarly, what I can write? Below the equicohesive temperature, then what you can write? Below the equicohesive temperature, grain boundary strength is greater than strength of your matrix. Okay. Above equicohesive temperature, just opposite. Strength of matrix is greater than strength of the grain boundary. And this is applicable during the creep failure actually. Now if there is a question, can you tell me? So why grain boundary become weaker at high temperature? I told you just few minutes before. Just tell me. Grain boundary sliding happens. Very good. Grain boundary become weaker, they will slide past each another. So it become weaker, no? Deformation is happening. That means. Because strength means what? Resistance to plastic deformation. But when grain boundary sliding is happening, deformation is happening. It cannot resist. So it is weaker. But there is another concept. Diffusion also happens at high temperature. So this point is very interesting. If you have finer grain and a coarser grain material, same composition, same phases, finer grain steel, coarse grain steel, and you want to apply it at high temperature. So which grain steel you need to use? Tell me. Just use your mind and tell me. Just take some time. Again, I am repeating the question. This is a very interesting question. You have two steel, same composition, same morphology, same grains. Grain size is different. One is smaller and one is bigger. So for high temperature application, suppose for example 600 degrees centigrade, 700 degrees centigrade. So which steel you are going to use, finer or coarser? And you need to justify it. Coarser, very good. Why? Because grain boundary number is less in coarser grain. So number of grain boundary less means grain boundary sliding will not happen. That is one part. And next part is diffusion will be also slow. Why? Why diffusion will be also slow? No distance. Forget about distance. Grain boundary is a region. It is a tunnel actually, tunnel. It is an empty space kind of thing where the atoms can easily move. That is the reason why I always told you go through the physical metallurgy lectures. I will share the videos. Just watch creep and this what is grain boundary. You will visualize what is actually grain boundary. Don't say grain boundary is only a defect and it is a what surface defect you people call basically. No, dislocation is a line defect and grain boundary is a surface defect people call. Anyways, just I will share you the video. That is very important. You may get question in exam also. So grain boundary is actually a tunnel. Tunnel means empty space is there. So if grain size is smaller, so number of grain boundary is more, tunnel is more, empty space is more. No? So more number of atoms and vacancy can move through that region easily. Or I can say grain boundaries are easy path for diffusion. That is a path which is easy. And you people know in nature everything wants to flow in a easy path always. So atoms wants to flow in a easy path. So it can flow in the grain boundaries because more number of grain boundaries means more diffusion will happen. And that leads to the creep failure. Okay, so high temperature creep failure is due to grain boundary sliding and due to high diffusion rate. So that is the reason why whenever you want to use a steel at high temperature, always choose coarse grain steel, not fine. But just opposite, you want a steel to be used at low temperature, means room temperature. So coarse grain steel is good or fine grain? Fine grain, very good. Why? Because more number of grain boundaries means more number of obstacles to the motion of dislocation. So strength will increase. That is called grain boundary strengthening or grain refinement strengthening or dislocation strengthening also you can say because of this. Okay. You can easily write in exam right now. Is it okay? This is a very interesting concept. This question sometimes they ask in the interview. Simple questions, but they will ask. If a person is very good in physical metallurgy, he will ask this question. What is creep? What is the difference between small grain size and big grain size? Huh. Okay, now this is a question again. Already we have discussed. Can you tell me 11 number? Creep in aluminium and silicon deoxidizer steel. That means to do deoxidation of steel, you have used either aluminium or you have used silicon. So which one is good?
Aluminium.
Question is, you need to use it at high temperature now. Not for machinability. You want to use it at high temperature. Yes, just think of it. You can answer it, I know. See, silicon, the moment you add silicon, it will form SiO2. The moment you add aluminum, it will form Al2O3. And atmosphere also contains some amount of nitrogen also. All the hints I have given now. Tell me. First condition is high temperature. That means creep will happen, maximum chance. And it may happen due to diffusion or grain boundary sliding. So, and already we discussed about the size of grain, smaller and finer. We need to use coarse grain. All the hint I have given, now tell me. So, silicon based steel is good. Yeah, actually answer is silicon based steel is good. Why? Because grain remain coarser in case of silicon deoxidation steel. But in case of aluminium deoxidation steel, aluminium will form aluminium oxide. That is one part. But aluminium also has very high affinity toward nitrogen. It will form aluminium nitride. And they will pin the grain boundary. And once the grain boundary will be pinned, grain size will remain smaller. So more number of grain boundaries will be available. So diffusion will be more. Grain boundary sliding will be also happen. So you have to look into the application, then only you can write. This is fine, you got the point? This is done. Okay, last is cast versus forged steel. Can you tell me now? You want a good creep resistance. Cast steel means just after melting and pouring, solidification. And forged means you are applying load on the material at high temperature. One hint is casting is basically done to give a shape, you know that. Pouring, we are pouring into the mold. And forging is done to remove the defects. Huh? Which one will provide you good creep resistance? Forged. Actually, when you do forging, the grain size will be finer. Because you are doing it at high temperature, then it will undergo small, that is called recrystallization will happen actually. Now what is the answer? Cast steel, because cast steel are bigger size grains. But you have to check, the application area is high temperature, creep. But if somebody will have room temperature application, then just opposite, forged steel is good. You have finer grain, you have more number of boundaries, more number of obstacles, this question cannot move. Done now? And last, fatigue, last question. Fatigue, I think you have heard about this, or fatigue means suppose this is a pen, this is a steel piece. I am just doing what? I am bending it continuously. Like this and like this I am bending. A time will come, it will become two part. It will fail. It will fail. But the load I have applied is also below the yield stress. This is also very interesting. But it will fail. That is called fatigue failure. Fatigue failure most probably happens in the railway tracks. How? The moment that means the rail wheel will come, load is applied, the moment it will pass away, it will relax. Again, and the railway track will come, and the railway wheel will come, right? And the time stress will be there. The moment it will cross away, again it will release. So that means it is a fluctuation. The load is applied in a fluctuated manner, not a constant manner. But in creep you have applied a constant load. But here the load is like this, increasing, decreasing, increasing, decreasing. And material will fail below the yield stress. That is called fatigue failure. So the answer is very simple. You have tried. Fine grain materials are basically good for fatigue resistance. Fine grain material. Just write one line. Fine grain material have high fatigue resistance. And there is one point you have to remember. Fatigue failure always starts from the surface. That is a very interesting point about fatigue failure. It will never start from the inside. It will start from the surface. That's why we will study one kind of heat treatment later. carburizing nitride. That is done to improve the fatigue strength actually. Okay, anyways, so this is done, I guess. So most chance you will get some questions in the exam from this part.